Welcome to ScienceCover.com. This session is on half-life. We'll cover what we mean by activity and what we mean by half-life, how radiation can be represented on a decay curve, and how carbon-14 can be used to tell the age of different objects. First, pause the video and complete the Do Now task. Let's check our answers. Radiation is caused by unstable nuclei. That is true. There are three types of radioactive particle. That is true. Alpha is made from a high-speed electron. That's false. A gamma ray is a type of electromagnetic wave. That is true. Ionizing radiation can damage and destroy cells. That is true. The nucleus was discovered by Charles Babbage. That is false. It was Ernst Rutherford. Smoke alarms use radiation to ionize air particles. That is true. When factories produce sheets of metal, alpha radiation is used to help monitor and maintain the thickness of the sheets. That is false. It is beta radiation. Carbon-12 is used to detect the age of organic material. That is false because it's carbon-14. And gamma radiation is used in gene therapy. That is false. Let's start by looking at what we mean by activity. When a radioactive material decays, the atoms of which it's made change into a new element. So every time one of these atoms decays, it'll become a new element and it'll give off an alpha or beta or gamma particle, and we'll be able to detect that. And the amount of times that this happens in a second is called the activity. So the activity of a radioactive material is just the number of nuclei that decay each second. Now, if we want to measure radiation, we use a device called a Geiger Counter. So a Geiger Counter clicks when it detects a radioactive particle. So to use a Geiger Counter, we'd place a source in front of the counter and we'd measure how many counts it picks up in 1 minute. Now if we divide that by 60, we'll find out how many it counted in a second. Now the activity of a source is always much higher than what we pick up with the Geiger counter, and this is because the source will give off radiation in 3 dimensions. So radiation will be given off forward, backwards, to the left, to the right, but we can only place the Geiger counter in one place, and this means it can only measure the radiation going in one specific direction. So the Geiger counter will always give a lower count than the activity of the source. When a Geiger counter is not pointing at a radioactive source, the count rate does not go to 0. This is because we're still detecting radiation. Now we call this radiation background radiation. So background radiation is any radiation that is always present due to either natural or man-made sources. Now you can see on the screen that background radiation is made up of different types of radiation, and radon gas makes up the largest source. Now radon gas is an alpha emitting gas and it comes from the ground. So anybody in jobs like mining who work underground gets exposed to more radon gas, and when you breathe this in, then it can decay and give off alpha radiation inside the lungs. We've got 12% being medical and x-rays from our background source. 12% of our background radiation comes from just food sources, 10% comes from cosmic rays, that's radiation from space, and 14% of our background radiation comes from the rocks, the bricks, and the soil that surround us. Now pause the video and attempt task 1. Let's check our answers. What is the activity of a substance? That is the number of radioactive nuclei that decay every second. What device do we use to measure the radiation? It is a Geiger counter. Describe how you would use the device in question 2. So to measure the background count, we'd keep the Geiger counter away from the source and measure the number of clicks in 60 seconds. Then we'd measure the count rate by placing the Geiger counter in front of the source and count the amount of clicks in 60 seconds. Then we take the background count away from the count rate to find the amount of clicks per minute from the source itself. Now if we then divide that value by 60, we can find the activity of the sample. Why is the activity of the sample higher than what is detected by the device? This is because radiation is given out in all directions by the source, but the Geiger counter will only pick up particles travelling through it and therefore in one direction. What is background radiation? This is radiation that's around us all of the time, that's given off from natural or man-made sources. Name some examples of background radiation. It could be radon gas, cosmic rays, bricks, clay, soil or stone, foods such as nuts or bananas, medical, fallout, nuclear waste. Now let's look at half-life and how this relates to decay curves. Radioactive substances do not stay radioactive forever. Bit by bit they decay, so we get less and less of the radioactive substance and more of a new element that's being formed. The half-life of a material is the length of time it takes half of the radioactive atoms to decay. So we can show this diagrammatically. If these 16 purple circles are represented by radioactive isotopes, the length of time that it takes for half of that 16, so 8 of them, to decay, will be the half-life. Now in another half-life, I would expect to drop from 8 radioactive atoms to 4 radioactive atoms. And in another half-life, I would expect to drop from 4 radioactive atoms to 2 radioactive atoms. Now the length of time that it takes to do each of these steps is the same. So if it takes 2 years to drop from 16 to 8 atoms, then it'll take 2 years to drop from 8 to 4, and it'll take another 2 years to drop from 4 to 2. However, if it takes 20 years to drop from 16 to 8, then we would expect it to take 20 years to drop from 8 to 4, and another 20 years to drop from 4 to 2. So this is what we mean when we talk about the half-life of a sample. How long does it take for half of the radioactive sample to decay? We can represent this kind of decay on a graph. So here you can see the number of half-lives plotted on the x-axis and the amount of radioactive atoms plotted on the y-axis. So we're starting with 16 radioactive atoms, and after 1 half-life we know we've dropped to 8. After 2 half-lives we've dropped to 4, after 3 half-lives to 2, and after 4 half-lives we've dropped to 1 radioactive atom. Now if you plot a line of best fit on this graph, you find that you don't get a straight line, you get a curve. So these graphs are called decay curves. And it doesn't matter what type of element we pick, we should see, as long as it's radioactive, a decay curve. Now we can change the x-axis to suit whichever element we are looking at. So imagine the source has a half-life of 5 years, then every 5 years the number of radioactive atoms will halve. So as you can see on this graph, we've put our x-axis to 5-year gaps, and so after 5 years we'll drop from 16 to 8. After another 5 years we'll drop from 8 to 4. After another 5 years we drop from 4 to 2. Now let's look at how we can find the half-life from one of these graphs. So first we need to select a point. Now I would suggest selecting the 0 time point because it's easy then to read the time of the x-axis. So you can see here that at 0 time has passed, we're starting with 100 radioactive particles. Now what we want to do is mark when this point is halved. So half of 100 radioactive particles is 50 radioactive particles. So let's read off the times that these two events occur. So I know I start at 100 and this is going to be a time of 0. And to drop to 50, if we read across the graph here, we can find that we reach 50 after about 2 years. So this means that the half-life of the graph is the difference between the 100 and the 50. So we're talking a 2-year gap to go from the first point to the second point. So therefore 2 years is the half-life of this graph. Pause the video now and try task 2. Let's go through the answers to task 2. Number 1, what is meant by the half-life of an element? It is the length of time for the activity of the element to fall by half, or for the length of time for the count rate of the element to fall by half. Number 2, a radioactive substance has a half-life of 40 years. What percentage will be left after 80 years? Well, after 40 years it should drop to 50%, so after 80 years it should drop to 25%. After 120 years it should drop to 12.5%. Question 3. On the graph below, mark 2 lines to help you calculate the half-life. So we should have a line coming across from 40 and down to 2, and a line coming down from 80 to 0. So the half-life is 2 days. How many counts are detected after 4 days? It should be 20 counts. How long does it take for the count rate to drop to 10 per minute? That would be 6 days. Number 4, draw a line of best fit on the graph. That can be seen in the diagram. Calculate the half-life of the sample. The half-life should be 60 seconds. Estimate how long it will take for the number of radioactive nuclei to fall to 200,000. It should take somewhere between 125 and 150 seconds. Now let's look at how we can use carbon-14 to date the age of different objects. We can use the decay curve of carbon-14 to estimate the age of an organic material. Plants and animals replenish carbon-14 throughout their lives, but when they die, the carbon decays and the amount found in the organism reduces. By working out how much is left, we can estimate the age of the organism, or at least when it died. We can also use a chain method to find out the age of a sample. Let's have a look at an example. A body is found in a burial chamber that has maintained 12.5% of its carbon-14. Estimate the age of the body. Carbon-14 has a half-life of 5,600 years. So we know that we're starting off with 100% the amount of carbon-14, and after one half-life, so that's 5,600 years, it should have dropped to 50%. After another half-life, it'll drop to 25%, and after another 12.5%. So this is 1, 2, 3 half-lives that have gone by. So that's 5,600 times by 3, and that gives us a total of 16,800 years. This method can also be used to estimate the age accurately. So a caveman is found with 3% of the regular carbon-14 sample present. Estimate how old we think the caveman is. So we know that when he died, he'll have had 100% the sample of carbon-14 in his body, and that'll drop to 50% after one half-life, 25% after two half-lives, 12.5% after 3, 6.25% after 4, 3.12% after 5, and after 6 half-lives it'll drop to 1.56. Now that's actually too far, because it says in the question he's only got 3% left. So we can ignore the last half-life that we've got here, because the 3.12 is much closer to his sample than the 1.56. So let's just ignore that last step and we'll stick with 5 half-lives. Now 5 half-lives is a total time of 28,000 years. But 3.12 is still a little bit bigger than 3%, so I might want to add an extra 1,000 years on just to bring the answer a little bit closer. Now this is still an estimate. It'll never give me an exact answer, but it will allow me to accurately estimate how old, in this case, the caveman's body is. Pause the video now to try task 3. Let's check our answers. The duck skeleton is found in the mud. It has 12.5% of its carbon-14 remaining. How old is the duck? There are 2 ways to answer this question. We can look at the graph and read across from 12.5%, and we should find an answer about 16 or 17,000 years. Or we could use the chain method to be more accurate and assume that the duck had 100% of the carbon-14 when it died, 50% after 5,400 years, 25% after 10,800 years. Therefore, after 16,200 years, it should have 12.5%. The asteroid contains uranium, which has dropped to 50% of its original activity. The half-life of uranium is known to be around 4.5 billion years. How old does this suggest the solar system will be? We can assume the asteroid formed at the same time as the solar system. So if it's down to 50% of its original activity and the half-life is 4.5 billion years, then the solar system should be about 4.5 billion years. A wooden spear is found to contain 6% of the regular carbon-14 sample present. Estimate the age of the spear. So if we read this off the graph, then we should find an answer somewhere in the range of 22,400 to 24,400 years.